Hello, everyone. My name is Zakhary Dichev, and today we'll be speaking about back pressure over the wire. And we'll particularly cover some of the things that might go wrong when you're trying to implement that concept in production. And why am I even talking about this, right? Over the last couple of years, I kind of touched quite a few systems that are distributed in nature and are most of the times kind of streaming in nature. And when you're working with architectures like that, the necessity for having back pressure in place a lot of times becomes quite obvious quite quickly, and in a not so pleasant way. So let's just dive right in, right? So we'll start by actually motivating the need for having such a protocol that's flow control aware in place. And we'll start with something very simple, right? It's just a case of sending messages between two systems that are on different network nodes. And our goals are particularly simple. We want to carry data from A to B, and we want to exhibit consistent performance characteristics when we are doing so, because we don't want to be fast some of the time. We want to be able to put hard constraints on the runtime characteristics of the system that's running in production, right? And we want to be doing actual work most of the time. So instead of wasting our CPU time on doing garbage collection, we want to be using the cycles to do the work that actually matters, which is processing messages, right? And of course, we want to fit within the constraints of the hardware we run on. The tools we'll be using, well, that's of course Scala, Akka Actors, the new Akka Remoting, which is not really that new anymore, with the underlying Aaron UDP transport, and protobuf serialization. So if we have to draw what we want to have, it kind of looks a bit like this, right? So we have two nodes that are sitting on separate machines in our network, and node 1 is just sending messages to node 2 over Akka Remoting. They're getting serialized into protobuf representation, getting carried over the network, and are processed by actor 2 on node 2, right? So if you have to translate that in code, a very simplistic version of it would sort of look like this, right? On the consumer side, pretty much we have an actor that takes some metrics classes. Those are CodeHail metrics classes. And in the receive method, we just simply get the message from the producer. We compute some statistics around the latency and the throughput on the consumer side, and then we sleep for 1 millisecond. So theoretically, given an infinitely fast producer, you might put a theoretical bound on the throughput of that consumer to be something around 1,000 messages per second, right? So on the producer side, you actually don't even need an actor. You can just have a stream that continuously emits an element and sends it to a resolved remote actor ref. And you might think that this is just fine, right? I mean, what could actually go wrong? And believe it or not, I've seen quite a few production systems that sort of had this notion in mind, but then they quickly realized that things don't really seem as they expected. So you don't actually need to dig deeper in order to see what the problem is here. You can just simply start by taking a quick look at the throughput on the consumer side, right? So this is the throughput on the consumer side measured over the span of nearly 5 minutes. And you can quickly see that, you know, our throughput is sort of hitting the 900 messages per second mark sometimes. And this is sort of what we would be expecting, right? But every now and then, we have these huge drops where our throughput goes to nearly 0 messages per second. And these drops are quite periodic and quite sharp. And looking at the latency, you know, it sort of grows linearly as well. So what is actually happening here? Well, think about it, right? Messages are delivered over UDP at an incredibly high rate. And our consumer mailbox, because it can't kind of keep up with the rate at which messages are arriving, is growing in size as time passes. And at that point, these messages are obviously stored in our heap. So what's happening is that our heap is ballooning in size, and now we're spending a lot more time doing garbage collection and wasting a lot of the CPU cycles doing garbage collection. So, of course, this results in degraded and, more importantly, unpredictable performance. Because these kind of garbage collection cycles are largely non-deterministic. So, you know, instead of having this picture that I showed you in the beginning, you sort of end up with something that looks a bit like this, right? And even worse. So, and in order to convince yourself that this is the case, you can actually take a look at the memory footprint over the life cycle of this run. And you would end up looking at something like this, right? Which shows that we start with a healthy heap of around a few hundred megabytes, but we quickly grow linearly in this sort of stepwise manner. And we end up with a heap that's close to 4 gigs. And obviously, that's not a healthy situation. You don't want to be in that scenario where you kind of are growing at that rate in terms of the heap occupancy. So, and to correlate that with the actual throughput, you can also take a look at the GC and CPU load statistics of, on the consumer during the life cycle of this run. And you'll quickly see that, you have these huge spikes where your GC activity is spiking up and your CPU load is hitting nearly 100%. And these are the exact moments when our throughput sort of goes to nearly 0. And you end up with this kind of vicious cycle of managing this heap, going into these sort of systemic GC pauses. And obviously, this is not a situation that you want to observe in production. So what are some of the ways to deal with the problem? Well, you can increase the memory as you need to, which of course is bounded by resource and practicality constraints. You simply can't be doing that forever, because I assume that you guys don't have infinite amount of money and space to kind of provision for that. And another thing that you can do is introduce a bounded buffer that drops data. And there is a bounded mailbox in Akka that you can use. You can use other sort of mailboxes as well. You can implement one yourself that sort of employs various heuristics for dropping messages when it's full. But this is highly prohibitive for some cases, because if you're doing sort of Snapchat or online multiplayer, you can allow yourself to drop a few messages here and there, and you can even sort of account for that. But if you're let's say an algo trading company that's sort of ingesting some market data feed and making decisions on that, you don't want to be in a position where you have to drop messages. You simply can't be doing that. Of course, another alternative is to introduce a protocol for requesting demand, which complicates things a bit. But let's actually take a look at how that would work out in this particular scenario in its very simplistic form. So instead of having the consumer simply being passive, we can turn things around a bit, and that's something that's recommended as a pattern in the Akka documentation. You can employ the work polling pattern where your consumer is effectively a lot more active, and it's actively asking the producer for the amount of work that it demands. So it's ready. It indicates that it's ready to process that much work, right? And this is actually a quite valid pattern. Its benefits are that it allows for dynamic scaling naturally, because you can spawn more consumers that simply kind of address the producer. You can introduce a cap on the size of your mailbox without dropping messages. And as a result of that, you prevent the system from running at its limits. And I'm sure that you've noticed that systems, much like human beings, exhibit their worst performance when they are pushed to the limit. Some of the drawbacks, however, are that it's not really trivial to implement. And this is a very kind of toy example, but so that's not hard. But implementing a reliable flow control aware protocol, it's not an easy task. And researchers have been focusing for that for quite some years. And arriving at a solution that's efficient and it's reliable, it's not a very easy task. Of course, it also introduced additional traffic overhead due to the control messages that you're sending. And in this scenario, we only have one type of control message, but depending on the guarantees that you want to provide in your protocol, you might end up with a lot more of these messages flying around because you might want to account for redelivery requests and whatnot. And of course, another important point of that, and it's not necessarily a drawback, but this only works if everybody plays along. And we'll see how that actually matters later on. But of course, if your consumer is requesting work from the producer, but the producer simply doesn't respect the protocol and just simply blasts messages at full speed, well, obviously that's not necessarily going to work. It's not going to work at all, actually. So, if you have to translate that in code in a very primitive way, on the consumer side, you can end up with something like this, right? So again, we have the consumer that takes the metrics classes that are used to produce the benchmarks. And it takes the producer path, which is an actor ref path. It tries to resolve it. And when it resolves it, it requests work from the producer. And this batch of work is capped at some kind of a predefined amount. And when messages arrive, effectively, we are again measuring some benchmarks. And we're sleeping for 1 millisecond, incrementing our counter of processed messages. And then we maybe request some work. And the maybe request work pretty much looks at whether we have processed the last batch of messages we've requested. And if that's the case, we send another request. And obviously, this is not extremely efficient because you can pipeline things a lot more efficiently. You can come up with a more efficient protocol for doing that. But just simply to illustrate what's the impact of that change, you can look at the comparison of the throughput between these two consumers, right? And you can quickly see that now we are hitting almost 900 messages per second, and we are not experiencing this variability in throughput that we were observing earlier. And our latency looks quite healthy as well, so it's not really growing in a linear fashion. And looking at your memory occupancy, you can quickly see that you have this sort of a healthy heap size that you're maintaining throughout the life cycle of this run, around 200 megabytes. And this obviously is a lot better than growing your heap to 4 gigs. And comparing the CPU load statistics and the garbage collection activity stats, you can also see that we are pretty much averaging around 10% of CPU load for the updated example. And we still have garbage collection activity, naturally, right? But this doesn't really put such a dent on our CPU utilization. So you have all of these spare cycles to sort of spend on the work that actually matters, which is crunching through these messages instead of just simply wasting these cycles on garbage collection activity. So what are some of the takeaways of that? Well, producers outpacing consumers can be a real problem. And this of course, can result in degraded and more importantly, unpredictable system performance. And it's difficult to diagnose, especially in stream processing pipelines, because you don't really know where the problem is happening. So you kind of need to be looking at all of your services and see exactly where this problem is happening. So having an end-to-end back pressure in place is a good way to avoid these problems. So enough with the 2 examples. Let's actually talk about an architecture that I worked on and that's running in production. Since let's consider some of the things that can go wrong, even when you're accounting for all those things and you're trying to kind of have flow control aware protocol in place. So the technologies that we'll be kind of using, it's Akka Streams, which I'm pretty sure most of you are familiar with that. It's a great toolkit from Lightband that adopts back pressure as a fundamental idea. And it provides you with the building blocks, so sinks and sources and combinators to. It provides you with these building blocks that allow you to construct quite complicated stream processing workflows. And of course, it sits on top of Akka actors, so that's what kind of makes it tick. And but the difference is that it's APIs typed, unlike the traditional Akka actors. And we'll be using also Alpaca, which is a collection of Akka Streams integration for third-party services. So these are pretty much collection of sinks and sources that allow you to produce to and consume from services like S3, RabbitMQ, Kafka, and whatnot. So it's a great kind of toolkit that allows you to sort of use these services as a data transfer fabric but consume from them and produce to them in a back-pressured way. So it allows you to incorporate the notion of back pressure in your processing pipelines. So let's get back to the example, right? I happened to work on this system a while back where it was characterized, it was a stream processing system that had various transformation phases over the data that was being ingested at the ingestion point. It was characterized by the fact that at the ingestion point, messages were arriving at an incredibly high rate. And they kind of needed to be processed at some point, right? It was not really critical when. They were going through various transformation phases that were in nature computationally intense. Naturally, the rate at which messages were arriving was higher than the rate of which they were going through the processing pipeline. So previous attempts at engineering that kind of system were based on Akka actors, where the separate processing stages were modeled as services that were pretty much remote actors deployed, and they were communicating through passing messages. Obviously, that didn't really work very well because it ended up happening that some of the messages were effectively DDoSing some of the services were DDoSing other services, and people started seeing a lot of problems with garbage collection pauses and whatnot happening in production, and pretty much systems or components of the systems going completely unresponsive. So the decision was taken to actually put Akka streams and use Alpaca, and namely the RabbitMQ reactive connector, to carry data from between these processing stages. So the solution sort of looked like this, right? Each processing stage was modeled as an Akka streams flow, and it was consuming from a reactive MQ, a RabbitMQ reactive source, and publishing to a sink. And pretty much looked like this, right? So the publisher was sending messages to the broker. They were getting queued onto the respective queue, and the consumer was through the back pressure Akka stream source was consuming messages from the RabbitMQ broker using and pressuring the broker through the QoS prefetch setting. And that's actually something that's important to touch upon. The way back pressure is implemented in the RabbitMQ connector for Akka is through the quality of serving settings, which allows you to effectively limit the number of unacknowledged messages that will be delivered from the broker to a consumer to a certain predefined amount. Which means that you can implement back pressure by means of simply hacking the message whenever you're done processing it, right? So this allows you to pretty much flow control the broker and say that, okay, I'm still not done with that message and I've already buffered, for example, 10 messages, don't send me any more. Obviously, that doesn't work with auto-hacking, but this hasn't been seen as such a huge problem. So it allows effectively the consumers to indicate to the broker that they cannot accept any more messages. So if you kind of need to sort of put that in code, put a very simple example that illustrates that in code, it would look a bit like this, right? On the consumer side, you have some queue settings that you're constructing, and then you have a AMQ source with a buffer size of 10, which means that you can have at most 10 unacknowledged messages that have entered your stream processing pipeline on the consumer. On the producer side, it's even simpler. You can construct a kind of an infinite source that just blasts messages to the AMQ sink, which effectively publishes to the broker. And you might think, or at least I thought, that this is just fine, right? This looks completely natural. RabbitMQ is a system that's been running in a lot of production environments, so it should be pretty okay. However, after I run some benchmarks on the consumer, I realized that, yes, indeed, we do have back pressure in place here. Everything's working normally, and our heap is fine. We don't have the problems that we saw earlier. Nevertheless, our throughput was not really consistent to what I was expecting. So there was quite a bit of variability in the throughput. And this kind of made me think, well, what is actually going on? So it turns out that on the broker, you can enable the RabbitMQ control management plugin, and that exposes you an API that allows you to look at various statistics around what's happening on the broker. So you can look at, ACK rates and whatnot. You can look at the size of your queues per queue, per connection, per consumer. So lots of useful data that you can look at. And the things that we are currently looking at is effectively stats from this API, from the broker, right? And what I observed is that the deliver rate and the publish rate were going up and down quite significantly. And the deliver rate, just for your information, is the rate at which messages are ACKed by the consumer, while the publish rate is the rate at which messages are persisted onto the broker. So why might that be happening? Well, it turns out that the broker works by maintaining a set of Erlang processes, right? And this Erlang process, much like Akka actors, communicate via message passing. They are asynchronous entities. And this message passing is effectively enabled by, of course, queues. These mailboxes or queues are they're not bounded, and they can grow if the rate of receiving messages from the network socket is actually quite high. And this is exactly what happens. So the memory alarms kind of go off on the broker, and the broker enters into this state of effectively not being able to ingest any more messages, and kind of the whole runtime sort of grinds to a halt. And it doesn't matter that this is Erlang and it's a completely different runtime, sort of the same problems apply, right? You end up with the same problems. It's just that now, although you've insured against the problem happening on your consumer, you kind of moved that problem from the consumer in your Java runtime to your middleware, which is the RabbitMQ broker. So you still don't have back pressure in place, right? Well, turns out that, the guys from Rabbit kind of noticed that problem, and they, well, not our particular problem, but the problem in general, and they implemented something that they call credit-based flow control on the broker, right? And this credit-based flow control is a feature that was introduced in RabbitMQ 2.8.0. And pretty much works as follows, right? So each of these asynchronous processes that are on the broker that are responsible for processing a message from the moment when it's read from the socket to the moment when it's persisted to longer-term storage, they kind of implemented the idea that each of these processes can issue credits to the processes that it receives messages from. And the sending process consumes that credit as it effectively sends messages. And in order to, when it runs out of credit, effectively, it cannot send more messages downstream unless it's granted more credit by any of the processes downstream. So it's effectively, if you distill that protocol, it kind of looks a lot like the work pooling pattern, right? It allows for the avoidance of effectively producers overloading consumers in that particular scenario. And so if you have to draw it, this kind of looks like this in a very kind of simplified manner. So as you go left to right, you're depleting the credit that you've been issued. And as you go right to left, credit is issued to you, right? So this effectively ends up in a situation where if the queue process, for example, is slower, the message store process is slow and cannot keep up with the rate at which the reader is reading off the network socket, this sort of back pressure will propagate all the way to effectively this reader process that reads off the network socket. And when that happens, well, and the reader process effectively stops or slows down, that back pressure that's occurring at that point will effectively be propagated over TCP to the producer side, right? So even if you simply bump up the version of RabbitMQ from the one that I was using to 3.6.13, you can quickly see that this sort of problems start to disappear, and you end up with a much more smooth publish and deliver rate that you're experiencing. So what are some of the takeaways of that? Well, it really takes only one non-compliant component to effectively ruin all of the efforts that you've put in order to implement that sort of flow-aware protocol. And if you're in doubt that something is happening, make sure to measure everything everywhere, right? And be aware of the implementations, of the implementation detail of the transfer protocol that you're using, because this is actually quite important. So be aware of what guarantees it provides, how it implements back pressure, to what extent, and what needs to be in place for all of that work. And of course, keep up to date with the development of the third-party components that you're using in production, because these protocols are sort of continuously developed, and a lot of improvements happened recently. So it's good to be on the mailing lists of, the developer organizations that are supporting these protocols and services in order to be catching up with the latest updates. So enough being said about Rabbit. It turns out that if you can effectively end up in situations where you have back pressure in place, but still you're experiencing some problems that are hard to diagnose, and you kind of wonder, where is that coming from? And that can very well happen if you are using Kafka as well. So let's actually look at an alternative approach of how that could be done, right? So we'll be using reactive Kafka. And again, this is a technology that's part of Alpaca, but it's just sitting in a different repo at the moment, I think. And it's pretty much implementation of an Akka Stream consumer and producers. Well, it implements the Kafka consumer and producer as Akka Stream source and sink. And the producer back pressure can be achieved through broker acknowledgements, while the consumer back pressure is achieved through the use of the pause and resume API. And this guarantees end-to-end back pressure, at least in the perfect scenario. And before we dive a bit deeper, let's actually consider what is the pause and resume API, which is the main facility that is used in order to implement back pressure on the consumer side for Kafka. So, if you've worked with Kafka, you probably know that the poll method on the Kafka consumer, especially in the native Java driver, needs to be called periodically for various reasons. For example, evocation of rebalance callbacks that you've hooked on this consumer. And posing a partition guarantees that a call to poll will not return any records for that particular partition. So if you're sharing your consumer amongst multiple partitions, multiple subscriptions, you want to have the facility of saying, okay, I'm not ready to process any more records for this particular partition, but yet again, I need to be calling poll. And that's why there is the pause API that pretty much allows you to say, okay, now I don't want, until this partition is resumed, I don't want to be receiving any more records for it, no matter whether I'm calling poll or not, right? And how often I'm calling it. So this pausing and resuming functionality pretty much allows you it's kind of the main facility that allows you to implement consumer back pressure for Kafka, and also be able to multiplex multiple subscriptions over one Kafka consumer while still sort of exercising flow control. So, how is that actually translated into Akka Streams on the implementation side, and how does that actually look like on Akka Streams? Well, so effectively, what's happening is that the consumer source stage, which is an Akka Stream source, it pretty much communicates with the consumer actor that's kind of an implementation detail. And this consumer actor might very well be shared amongst multiple source stages, right? So this consumer actor is responsible for mainly doing two things. One is it maintains an internal timer task that periodically calls poll at some configurable amount. And when it's calling poll, it actually checks whether there is any kind of demand that's indicated from any of the Akka streams that are in membership of this consumer actor. And if there's no demand, or for the partitions that there is no demand, before poll is called, these partitions will be paused. So this happens periodically, right? And this poll call is effectively kind of piped to the Kafka driver. And when demand is indicated from any Akka stream that is hooked to this consumer actor, what's happening is that the demand request arrives in a form of a message to the actor. That partition is unpaused. If it's paused, the particular partition for which the demand request is in, and some records are fetched from the Kafka driver, and they are sort of delivered, and they enter the stream, right? So this is how pretty much it works internally from a bird's eye perspective. So on the consumer side, like if you want to implement that, let's actually look at something very peculiar that can happen. So imagine you have the following piece of code. So you have configured your periodic poll interval to be 50 milliseconds. So no matter whether you have demand or not, your actor will be calling this poll method on the Kafka consumer every 50 milliseconds. And then you have the following kind of stream, right? You have a consumer that is throttled at 100 milliseconds, and you're simply doing some processing on the messages that you're receiving. In this particular case, you're mostly doing nothing, right? So if you run that code and you have Kafka deployed, you see that your consumer rate sort of looks like this, right? So it's not something unexpected. However, if you dig a bit deeper, you end up with the following stats, right? So if you look, so pretty much what we're looking at the moment is the messages that the consumer is receiving. So the number of messages that are entering the stream on the consumer side versus the number of messages that are sent out from the broker, right? In terms of, so the number of bytes really that are sort of leaving the broker. And it's kind of interesting to see that, you know, at 50 milliseconds of a poll interval, twice as many messages are leaving the broker as are entering the consumer, right? So once you bump this setting to be 10 minutes instead of 50 milliseconds, you end up with a situation where you have roughly, roughly the same number of messages that are leaving the broker and entering the consumer. So, you know, the first time I kind of saw that, I was like, why is this happening? This is even a bit surreal, right? I mean, where are these other messages going? Like, why is that happening? Well, it turns out that there's actually an explanation for that as well. On the Kafka driver side, the native Java driver, there is something that's called the prefetch logic on the fetcher, right? And this is a pretty interesting piece of logic that's happening. Effectively, the Kafka driver, and this is kind of something that's beyond the realms of Akka and the streams toolkit. So this is happening in the Java driver, right? And the Kafka Java driver effectively kind of pipes all pull requests to a component called the fetcher that's responsible for contacting the broker and communicating with the broker directly. So what's happening when a poll call arrives? Well, when a poll call arrives and all partitions are resumed, aka unpaused, what's happening is that the fetcher issues a fetch request to the broker and fetches a batch of records, right? So the next batch of records. And this amount of batch of records is configurable, but that's another point. So when these records are returned from the broker, what's happening is that before they're returned to the actual driver, another fetch request is initiated. And this is just for the purpose of actually pipelining things, right? You want to be a bit more efficient. So it's kind of like a bit of like a betting machine. It tries to make a bet that, you know, soon enough you need the other records. So it prefetches them. But because there is no demand for these records just yet, after the first batch of records is returned to the Kafka driver, what's happening is that the second batch of prefetched records are now buffered on the fetcher internally, right? And when a call to pause is effectively triggered on that particular partition, and then POW follows again, what's happening is that because there is not a very clear idea of what should happen with these records, because our partition now is paused, in order to free up space, these records are thrown. So how does that actually relate? This smart optimization, how does it actually relate with our particular weird behavior that we are experiencing and seeing? Well, so this is the prefetch fallacy, or at least I call it that way. So imagine in our situation that we had earlier, what's happening is that at our actor, effectively, a demand-driven poll arrives at, so imagine this timeline is 100 milliseconds, so a chunk of 100 milliseconds of time, right? And at 0 milliseconds, a demand-driven poll arrives on our actor. So now we initiate a fetch request through the fetcher, and we fetch records 1, 2, and 3, and they are served to the stream. However, records 4, 5, and 6 that are prefetched are buffered onto the fetcher. Then a timer-driven poll arrives at time 50 milliseconds, let's say. And because now there is no demand for this particular partition, remember this demand comes every 100 milliseconds because of the throttle. What happens is that this partition is paused, right? But then POW is called again because that's what the timer is responsible for. And when that POW is called, what's happening is that all the buffered data, records 4, 5, and 6, is effectively thrown away. So when a demand-driven POW arrives again at 100 milliseconds, effectively what's going on is that this partition is unpaused again, and now records 4, 5, and 6 are fetched once again. So effectively, the end result is that this data is traveling over the network twice instead of just once in this particular scenario. So what is the end result? Well, this kind of results in increased fetcher activity due to duplicate records being transferred over the wire. And of course, this increases the load on your Kafka broker itself, which is not really what you want to do, especially when you're not really making use of this data. And of course, that also puts some pressure on the network infrastructure that you're running. And if you are running on some more expensive cloud service that kind of accounts for these data rates, you can quickly see yourself spending a lot more money on because of the duplicate data transfers. And you know, this is a very simple example just for the purpose of explaining what's actually happening. But this particular problem can lead to very unpredictable patterns of record transfers, because currently what we're looking at is effectively very statically a demand pattern on the stream that can be described in a very sort of static manner, right? It's very periodic, it's very consistent. But you know, that's not how real-world systems are. They kind of go through spikes of activity, and it could be the case that it's not that you only demand data every 100 milliseconds. It could be a lot more dynamic sort of interaction with the broker. And on top of that, if you have more than one consumer being hooked to this particular actor, you can quickly end up with a situation where your patterns of data transfers are very, very unpredictable, and you're seeing some duplication, but it's really hard to identify why this is happening. So what are some of the conclusions that kind of can be taken from this talk? Well, be aware of when and if you actually need back pressure, right? So consider your communication patterns between your services quite carefully. And in case you kind of account for some problems that are occurring due to kind of consumers not being able to keep up with producers, then it's probably a good time to consider implementing some kind of back pressure protocol. And provide means for continuous monitoring. So nowadays there's a lot of tools that can allow you to sort of introspect on your services. So there are service meshes that allow you near like cost-free monitoring of services deployed in Docker, and you can use these tools in order to diagnose problems like that. And of course, be aware of hidden dragons, because a lot of the implementation details of these systems is actually quite complicated, and you can never be sure how this kind of particularly ties with the assumptions that you are making on your end of the system, right? So it's important to kind of dig deep into the implementation and see what kind of guarantees your data transfer fabric is providing you. So you kind of don't end up observing problems like that. And of course, keep up with protocol development. So these protocols are developed constantly. There is a very welcoming community of people that are working on Kafka and that are working on Akka and Rabbit, and they are always ready to sort of answer questions, and they're very welcoming to contributions. And in case you experience problems like that, you can always submit, for example, a proposal for improvement for Kafka, and that will be taken into account. For example, this particular problem, there was a KIP that I submitted, and the PR is still in review, but but at least they kind of paid attention, identified the problem, and they are working towards some kind of a solution. So these are some of the problems that I've experienced when working with distributed systems, and particularly when trying to work with back pressure protocols. Thank you for the time. And
hi, in the example with connecting through RabbitMQ, I didn't notice on the producer side what keeps it from overflowing the memory. What stops it sending the signals when RabbitMQ stops receiving them? Do you get a point?
I do get the point. When RabbitMQ stops receiving them?
Yes, when RabbitMQ stops receiving the messages, what prevents the producer actor from overflowing the memory?
Well, effectively, I don't think that we have an actor in this particular example. I think it's just a stream, right? So I'm not sure how it's internally implemented. Right, you're talking about this, right? Mm-hmm. Well, first of all, in the case of, if you have back pressure on the broker, right, this will effectively get propagated through TCPs.
Okay, I see. It's not just an actor, it's a specialized kind of thing. Okay, thank you.
Yeah.
May I continue with the same question? Here you have just a toy example where your source on producer is just emitting an infinite stream of test data. So it always can react to back pressure and limit its rate. But what is going to happen if you not getting this data from nowhere, but from some real third-party system? I mean that on production the data flows from outside. This outside client does not support back pressure. So in the variant with Kafka, I understand that all the if your producer is faster than consumer, all that messages would be stored on disk by Kafka. In the first case, when you are using RabbitMQ, your back pressure goes right to the producer, and if producer is unable to limit its rate because it's flowing without any limits from outside, then I think we'll see the same charts with garbage connector, etc., but on producer. So you just pushed your back pressure signal to the producer. will it handle it somehow with RabbitMQ variant, just like with Kafka variant?
Well, think about it. I mean, if so, first of all, at this point, like if you're implementing end-to-end back pressure within your system, right, within what you can control, it's important to take into account that you kind of need to speak the same protocol, right? So you need to ensure yourself that your producer is aware of that. If, for example, you have a producer that's outside the realm of whatever you are, whatever you're controlling, yes, that might very well happen, depending on how the producer is implemented, right? But let's just illustrate that with a very simple example. You have let's say you have a REST API at your ingestion point, right? And that's where you're receiving stuff from the producer. And this REST API is implemented in such a way that it kind of supports back pressure, right? So if you're using Akka HTTP, for example, this is a back pressured consumer site, right? And on the producer side, that's outside the realm of what you're controlling. I mean, what could potentially be there? I mean, a tight loop that pretty much banks out REST requests. Well, if that happens, then obviously your loop will effectively halt at some point, because the back pressure will be propagated through TCP. You're not going to be able to write to that socket anymore, right? And if you are effectively, it doesn't matter whether you're using synchronous or asynchronous sockets. If it's a synchronous socket, then you effectively block on your write method. If it's asynchronous socket, it will return you an error that would block or whatever when you're trying to write more data, and you're just simply not going to be able to write the data. So, in any case, they either are not implementing that and not respecting that protocol, and then you can't really do much about it, but you care about the stability of your particular system. Or in an alternative scenario, most of the cases, if they are using a protocol that's actually flow control enabled, then this should not be a problem. And thankfully, things like TCP is, it has flow control from the get-go. So
yeah, but maybe if it's already went so far that TCP is limiting our rate, we are already having the same problems on producer. What I wanted to state is that these two examples are not exactly equivalent. In the means that in first example we pushed the back pressure up to the edge of the producer rate is producing. On the second example, we pushed this back pressure signal up to Kafka, and Kafka is used just like a buffer for
Right. No, not necessarily, because you can effectively tweak your Kafka producer to use broker acknowledgements. So if your Kafka is sort of slow at ingesting these messages, or you put a hard limit on the kind of messages, the size of messages that it can ingest, then you can back pressure your producers through the acknowledgements of the broker. So again, you can put a hard bound on that, and you can implement.
Yeah,
that.
yeah, it can be. Okay, thank you.
Yeah, thank you for interesting topic. And my question is, you showed a few examples of solving the problem. So regarding the message broker that you picked up for your solution, so did you try it, or did you look for another broker implementations? Did they know about the problem, and do they have already an ability in their current versions to solve your problem?
You mean other technologies?
Yeah.
Well, I have not really. That's kind of the tech stack I have worked with, and these problems sort of arose from real production environments, and it's kind of hard, to be honest, to just kind of convince these people, okay, you do want to switch now, but I've looked at like other brokers and read about them, and to be completely honest, I haven't really dug quite deep into that, but I assume, most of these messaging queues work by surprise maintaining a bunch of queues in there, right? So, it's important to be careful with the size of these queues.
Hi, quick question. Will you elaborate a bit into monitoring and debugging tools? Just name a few in each level, particularly if you suggest something for monitoring akka, actors, queue, mailbox sizes, some metric tools, if there are any that you're using. Thanks.
Right. Well, I haven't really particularly gone into monitoring mailbox sizes and whatnot. I think Lightband has sort of a solution for that. I'm not exactly sure whether it's commercial or not. There was, in terms of regarding the monitoring of streams, there was a really nice talk, I think a few years ago by a guy in London, I think at Scala Exchange, where he was explaining about the framework that he wrote for monitoring Akka streams flows. What I mostly do is you know, instrumenting some code on the in my services, and you know, taking a look at metrics such as throughput and that kind of stuff. And if I see something fishy there, I'll dig deeper and actually spin up a profiler and look at, you know, the heap, what's happening with garbage collection and that kind of stuff. And these are all sort of macro things, right? If you're looking for more fine-grained performance, you can, you know, you can take a look at tools like vTune and stuff like that, inspect memory caches, CPU caches, and whatnot. With respect to monitoring brokers, you know, RabbitMQ has a really nice API, as I mentioned. Kafka, I think, has a solution for monitoring that stuff as well, and interrogating on sort of the log and that kind of data. There are service meshes that are quite nice, so things like Linkerd, they allow you to, you know, instrument a lot of stuff nearly for free on the, for example, HTTP request level. You know, how many requests are going through, what's the rate, what's the success rate, and whatnot. And I know these guys are effectively working for supporting alternative protocols like RabbitMQ and Kafka. So this will be quite a nice development that will be great to see in the future. But yeah, generally it's just monitoring the health of the particular service and then digging into most of these systems that are, you know, sort of data fabric system like Kafka and RabbitMQ and whatnot. They all have some sort of exposing stats because naturally this is very important. No more questions? I think.
Sorry, one more question. Do you have any knowledge about issues with Redis? Some kind of issues, but with Redis.
I've used Redis a while back, and I really don't particularly know any of these details around it. But it's just a cache, right? I'm not entirely sure how the situation is there. Okay, well, thank you again for listening.